All right, so the last video ended with a sign analysis for velocity, so we could answer part A. And we decided that if velocity is positive on the interval 0 to pi over 3, that means the particle is moving to the right for time 0 to pi over 3, and the particle is moving left for time pi over 3 to pi over 2. The particle is stopped at the exact moments when time equals 0 and time equals pi over 3. You may have seen a video, which I've now deleted, where I failed to integrate properly to do part B. So here's a much better work for part B coming up. All right, so part B, what is the particle's displacement? So I had all the correct integrals, I just messed up my antiderivative afterward. So we're going to integrate the velocity to get displacement. So pi over 2, from 0 to pi over 2, 6 sine of 3t dt. I don't have to worry about signs or where the velocity changes from positive to negative. I just straight up integrate. So I'm going to need a substitution. I'm going to need an antiderivative. You might make a substitution. You can make the substitution u equals 3t. So du over 3 is dt. And I'll get that this is going to be 6 over 3. The antiderivative of sine is negative cosine. This is going to be negative 6 over 3 cosine of 3t. And I have to evaluate that from 0 to pi over 2. So this is negative 2 cosine 3t from 0 to pi over 2. So that's negative 2. In the last video, if you saw it, I accidentally used the negative twice. I'm going to do it correctly this time. So I'm going to factor that negative 6/3 out to the front. This is going to be cosine of 3t. That's cosine of 3 pi over 2 is 0, minus the cosine of 0, which is 1. And I get my displacement is negative 2 times negative 1 equals positive 2. So my answer to part B would be that the displacement is 2. So if the original position, if x of 0, x for the position function, t meaning 0 meaning time 0, if x of 0 was 3, then x of my ending time was pi over 2, is going to be the initial position, the 3, plus the displacement, which is 5. Well, that's in bold at the bottom of your first page, that ending position is initial position plus displacement. Okay, so remember this antiderivative, because I'm going to erase the whiteboard and come back to answer part C. And for part C, I need the total distance traveled by the particle. Notice the distance the particle travels. I'm not even going to be thinking about that 3. Specifically, from the time it leaves at time 0 to the time it stops at pi over 2, how much distance has it covered? So if you thought about the particle walking, how many steps has it walked? Even if some of them are backward and some of them are forward. So if I had a calculator, I could use my calculator and evaluate the absolute value, the integral from 0 to pi over 2, the absolute value of the velocity function. And you will find that there are places on the AP test where you can just type this answer and you'll be done. You might be typing it under your calculator, or you might simply be writing this expression as your answer. And that's great. If I don't have a calculator, however, I'm going to have to perform this breaking up of my velocity function by hand. So we've already done most of the analysis that will help us do that. We know that the velocity changes from positive to negative at pi over 3. So what's important there is that the area under the velocity curve between 0 and pi over 3 is going to be positive because the velocity is positive on that interval. I'm just going to write v of t. And that if I integrate from pi over 3 to pi over 2, for that whole interval, the velocity curve is underneath the time axis. So that all of that area is negative, and my area result is going to be negative. So I'm going to either, I could subtract the next integral, or I'm just going to show that I'm going to take the absolute value because I know it's going to be positive. Oops, not 0. This part I'm going to have to integrate from pi over 2 to pi over 3. No, pi over 3 to pi over 2. I'm just going to call it v of t dt. And I know that result's going to be negative, so I'm going to put it in absolute value bars so that it becomes positive. So that's good. I know this antiderivative already. That's negative 2 cosine of 3t, evaluated from 0 to pi over 3, plus the absolute value of negative 2 cosine 3t, evaluated from pi over 3 to pi over 2. So I'm going to move some of this stuff out of the way and then evaluate this integral. All right, so here I go. And this is negative 2 times the cosine of 3 times pi over 3 is pi. And the cosine of pi is 0. So this is going to be negative 2. Sorry, the cosine of pi is negative 1. Minus negative 2 cosine of 0, which is just 1, plus this next part I'm going to put in big absolute value bars. It's going to be negative 2 times the cosine of pi over 2 times 3 is 3 pi over 2. The cosine of 3 pi over 2 is 0. So this is going to be negative 2 times 0 minus negative 2 cosine of 3 times pi over 3 is pi. Nope. 3 times pi over 3 is pi, and I need to take the cosine of pi, which is negative 1. Look at all those negatives in there. That's a lot to mess around with. Okay, so this is positive 2 minus 0 plus the absolute value of 0 minus positive 2. So it's going to be 2 plus another 2, which makes 4. So the displacement was 2. The total distance traveled was 4. All right, so what does this mean for us in chapter 7? Remember that integrals just came from wanting to add up a bunch of areas of rectangles, and we got those areas of rectangles by multiplying a base times a height. Well, it turns out you can use an integral to model summing up a whole bunch of products of two things. What's that really useful for? It really helps us when we want to find distance traveled, because usually we just multiply the speed times the time, but if speed is always changing, then I have to like break it up and do teeny tiny multiplications, speed times time, plus speed times time, plus speed times time, to accumulate all of those little products. That's what integrals are good for. So this is our chapter to practice using an integral to do this for us. So if you can think, if you have a quantity you want to find the value of, and you can write it as a product, even though like if you're the function you're trying to find the area under changes, just imagine finding the area under a teeny tiny part of the curve and adding it to an area about under the next teeny tiny part of the curve. That's what an integral does for us. So if you can think about what you want to find as a product and then think of it as a Riemann sum, adding up a bunch of those products, then we can translate that Riemann sum into a definite integral. So here's an example. This one's from your textbook. If I know the rate at which potatoes are consumed in some country, can I find the total number of potatoes that are consumed over some time period? So imagine this. This is the rate at which potatoes are consumed, and that's measured in millions of bushels of potatoes per year. So that doesn't tell me how many potatoes got eaten, but if I could multiply this number of potatoes per year, millions of bushels of potatoes per year, times a time interval, then I would get the number of potatoes eaten on that time interval. I can't just multiply the rate times the time because the rate keeps changing. Notice this is a function of t. It has a t up here in the variable. That means I can't treat it like a constant. It's not like back in, middle school when you wanted to find out how far something had gone, the speed was always a constant. You just multiplied it by the time. So this is what I want to figure out. I want to multiply the rate at which potatoes are consumed times the time interval that I want to measure over. And if I want to do that over and over very small time periods and then add up all the numbers of potatoes that got consumed, that's what I want to do. So I could think of this as like a Riemann sum. That's going to help me think of how to write my integral. That's going to be rate, which is c of t, times a very small change in time, which I'm going to call dt. These limits, well, maybe you didn't know those were limits. If my integral is based on the variable t, then my limits have to be time values. So I'm going to look back through my problem and see what time period do I really care about. T is measured in years since the beginning of 1970. So the beginning of 1972 is time 2. And the end of 1973, like the moment 1973 ends and 1974 begins, is time 4. You can use your calculator to evaluate this. It'll give you the number of potatoes consumed in this country between 1972 and the very end of 1973.